Good morning, everybody, and very welcome to the midterm event for In2Track3. Some of you know the project very well, some of you don't, so we will make a short fly-in to make sure that you are on board with what we are doing. The agenda for today is this. You have seen it when you signed up, so I won't go through that in too much detail right now. But there will be a short part with more from me and Sébastien Denis, who is our project. And then we'll close right before or on 11 o'clock. So very welcome, everybody. And now I would like to hand over to Sébastien Denis, our project officer. Welcome, Sébastien.
Thank you, Pernia, and welcome everyone to this midterm conference. Let me share quickly my screen, and I guess everyone can now see it in the presentation mode. So indeed, I'm Sébastien Denis. I'm working for In2Track3 as a program manager, and so there's somehow a bit of confusion, as you have seen in the agenda, that I'm Sébastien Denis, Shift2Rail project officer. So it's what I would like maybe to clarify first. So In2Track3, Shift2Rail, the differences. So basically In2Track3, this is simply the successor of Shift2Rail joint undertaking. So it remains a European private-public partnership for research and innovation, but this time under the Horizon Europe program and not under H2020. The objective remains the same, so this partnership aims to accelerate research and development in innovative technologies and operational solutions. Okay. So this is clarifying a bit the difference between In2Track3 and Shift2Rail. Regarding my position, so I'm indeed a project officer in the context of In2Track3, but however, In2Track3 is a block in an integrated program dealing with infrastructure, research, and innovation. And it's maybe from there that I would like to start my presentation to explain a little bit where In2Track3 is fitting into Europe's Shift2Rail / In2Track3 program. So the infrastructure program is so-called IP3. This is a cost-efficient and reliable high-capacity infrastructure. This is a research program of about 150 million euros, and I would say approximately 55-45 ratio between the funds that are given by the Commission, 45%, and the money that is provided by our members. Our members, you have an extract here. So this is basically the main infrastructure manager, operators, manufacturers, solution provider, institute, etc. of the European sector. Okay. How this program has been divided? It has been divided somehow in three main areas. And those areas are so-called integrated technical demonstrators. So there are 11 technical demonstrators. The first block from TD 3.1 to 3.5 are covering mainly the infrastructure aspect. So basically the switching crossing, the tracks, the bridge and tunnels, both inspection, etc. Both for the current solution that we are going to enhance, but also looking at more innovative concepts and technologies up to 30 years. So this is so-called the next generation of the solution. A second area is more linked to the intelligent asset management with some acronym that I will not detail, but basically it's some research on the data collection, then on the data processing, and then what we do with the data. So basically prescriptive maintenance, support for decision making, etc. And the last aspect is more touching the enhanced energy topic with smart metering energy, but also smart grid. Okay. So today we are in the context of the first integrated demonstrator. Okay, so for the infrastructure part. And as I mentioned, In2Track3 is only a block of this program. So the work started in 2015 with a so-called Lighthouse project In2Rail that paved the way basically on the main research area that the next project have been somehow exploited and continued to bring it higher level of maturity. There have been 3 calls for members that were reserved for members, the series of In2Track starting in 2016, In2Track2, its successor, and In2Track3. I don't go obviously into the details of In2Track3 that will be presented by Pernilla and the consortium, but however, in the approach, it is, I would say, a start at low tier level, so concept, ideas, etc. And then it has been step by step bring to higher tier level. And within In2Track3, we are aiming to reach maturity that will bring the solution for the market uptake. Around this main research area that were supported by the CFMs, there have been some so-called open calls, so some call for proposal reserved for the non-members. So there have been S-code that were mainly dealing with innovative concept for new switch and crossings. We've been working with assets for rail on bridges and tunnel inspection. And now we have one open call that is still open. This is the project In2Zone that is dealing with research on transition zone. And it's very important to emphasize today that those projects are tightly working together in a close collaboration. So this is not, I would say, standalone project. It's really a full collaboration between the CFM project, the members project, and the non-members project, with that have the same objectives, and this will be most probably presented by the colleagues of In2Track3 later on. So saying so, I would also like to present a little bit what is coming next, because In2Track3 will end in 2023, but obviously it will not end the research in Europe's rail regarding this area of investigation. So Europe's rail has been divided. So the next program that is starting now, basically, it has been divided in 7 areas, so-called flagship project, and is dealing somehow with the same areas of research that Shift Railway supported. However, the structure is slightly different, and the objective is to aim even more digitalization of the sector and even more greener solution. And in this context, in this program, there is one specific project that is so-called Intelligent and Integrated Asset Management that is currently under grant agreement preparation that will take over most of the results of In2Track3, either to bring them to higher maturity level, so really like industrialization, etc., but also to investigate some new topics, new areas of research that were starting in the context of In2Track3 and the other project. So FP3, the flagship project 3, that's currently under preparation of signature, will be the next project that will tackle all this infrastructure problematic and also innovation into the next program. Before giving back the floor to Pernilla, I would like first of all thank her for the organization of this very important conference. Despite the obligation to organize it, I think it's really a very good opportunity for the consortium to present their intermediary result. And so I'm wishing to everyone a very pleasant morning with the partners of the consortium to have a look on what has been done so far and what are the plans for the next year of the project. Thank you very much.
Thank you very much, Sebastian. And I hope everyone can feel that they have some background on the framework that we are working within. In2Track3 is part of a small part of a large framework program, and this is now I think everyone has gotten a good idea of what it is and also what it will become. This is the agenda for today. I will make a short overview now, and then we will go over to the 3 parts that we have chosen to cover. That doesn't mean that this is all we do. We don't do anything else. This is only what matters. That is not true. We do a lot of things that really, really matter. But in order for you, I mean, the meaning with the midterm event is to reach as many as possible with the research that we do. And in order to do that, we wanted to have an online meeting to start with, and also to have fairly short so that most people can just participate and it won't take too much of your time, and you will still get some vivid snapshots on what we are doing. There is very much more than this to the project, as you will see. So we have chosen to focus on 3 areas: monitoring and assessment, whole system model, and rail inspection. But who are we? We are 26 partners in the project. We are spread across Europe. We have different areas where we work. Some of us are universities, some are infrastructure managers, others have products that they develop and want to enhance or improve in order to reach new and more or grab more of the market shares. We have started in January 2020. And as Sebastian said, we will finish in December 2023. This is not up for negotiation. We cannot say that we like to do this too, because we really enjoy this and we want to prolong things a bit, because everything ends at December 2023. And everything that comes after that will be Europe's rail, in which, as Sebastian mentioned, our research will be taken forward. Some of it, not all, but some. We have a pretty wide coverage with our participants. As I mentioned, we have infrastructure owners, managers, and operators, the ones mentioned here. Large companies or authorities, government bodies that have as their purpose to make the railway run efficiently and smoothly, and who are very much interested in getting the new technology and knowing more about how we can do our respective railways and system better, cheaper, more cost efficient, and increase the capacity, if you remember the overall goals that we have. We have a number of universities and research R&D centers. These are the ones that are our partners, who are actively contract partners in the project. In addition to these universities and R&D centers, we have a number of universities who are third-party companies for instance, Trafikverket, Network Rail, and a few others. So there are twice as many universities as in this picture, actually, who are connected to us to vouch for us doing the proper research the proper way. And as I mentioned, we have these industry partners too. Companies who have products that they want to develop, test, further enhance, or anything that might be useful and to which they are interested in using the science and develop within the framework of the project. I think having these 3 parts of the infrastructure industry in our project is a great strength. And it's the size of the 3 parts is more or less the same, which gives we cover a lot of the railway food chain, and we have equal strength in each of the 3 parts, which I think is an important part for us. But the objectives, the overall goal is to build up under the IP3 umbrella a cost-efficient and reliable high-capacity infrastructure. Cost-efficient, reliable, high capacity. That's the keywords that we're supposed to build up under. And if we try and take this down a small notch, what do? We try and increase availability and reliability. We work to enhance railway performance. and to reduce railway life cycle cost. This is still pretty high level, right? So we have taken it down, of course, one or two or even more notches. For instance, how do we increase availability and reliability? Well, we try and do that by reducing system complexity, predictability in operations and maintenance. We have a large focus on predictive maintenance in different aspects of railway. And by have an increasingly robust we are reaching out to increase availability and reliability. The next point is to enhance railway performance. How do we in In2Track3 try and do that? Well, we try to improve the noise and vibration conditions, for instance. We try to improve the passenger experience, the comfort, how nice is it to ride by the train, basically. And that is also connected to noise and vibrations, of course, because vibrations when you ride a train is not really nice, and not noise when you live nearby, for instance. So we look at those parts and more. And to reduce the railway life cycle cost, we have parts of our project that we have improved inspection and maintenance, new track systems. We try and find new innovative ways of making the track systems. We want to reduce climate impact. We have some parts that work with that. Unfortunately, this is not a large part of the project, but it's in there and it's very, very important. This is still pretty high level. So what is it actually that we do? Well, one thing that we do that is easy to see, that is tangible and well, something to look at, feel, touch, if you're in the right place at the right time, are our demonstrators. Like Sebastian said, we have the expectations on this project is to continue work in In2Track2 and In2Track, and even that before that into rail, and to increase the TRL levels. I believe most of you are familiar with those, where the lowest level in our project is TRL 4, where we have the technology validated in lab, and the highest is TRL 7, where we have the system prototype out in the field. Most of our demonstrators are actually on TRL 7, 27. I think, I'm guessing now, but I think the largest, big of those are the ones up to the left is the new slab track solution that we have installed in the Swedish railway. But we also have really small ones, like down to the left, where we try and just put a tiny bit of material on the railway or on the rail itself, just to see, does this work for fixing broken railway? If there are just like small damages, maybe not. It's out in the track being tested, TRL 7. But we also have other things, materials that are intelligent materials that can send signals and show condition of the rail or the sleepers or other things, which is also very interesting, which was presented at InnoTrans also. It's in the middle bottom. And up on the top, we look at the non-chemical ways to master vegetation. That's one of the ways that we try to improve the LCC aspect of things. Is it possible to do something else than to just spray the side of the railway with pesticides? Well, we think so, and we want to try and have a look at it. High-speed railway is also coming big, and we need to make sure that our bridges that they can withstand the load that comes with the high-speed bridges, high-speed trains, I'm sorry. And that's also what we're looking at with the physical dampers that we have installed in the north of Sweden. So this is like a brief overview of other things that we do in this project and which are not part of this presentation today, but are also small snapshots of what are we doing really and how do we do it. So what do we do then? How do we get these results out? Well, we have In2Track3 at certain TRL levels. We are supposed to be at TRL 7 for many of our exploitable results. And the first, what do we do? How do we do it to try and get the exploitation of these results? Well, we started about a year ago, where we had our first in results, where we had a short description of potential, what could this be? All partners have been involved and have been given their opinion on what their individual performance in the project. What is there anything here that we can exploit and that can be something useful to industry? Everyone was involved in that. Now we are halfway. We have started to narrow it down with a more smaller number of participants, prioritizing the key exploitable results, not all exploitable results, but a few. And then eventually we will have a list of our exploitable results to take further. And I will tell you more about in the closing how we will do that. But now I would like to hand over to our first technical presenter for today. So please, for monitoring and assessment, excuse me. For monitoring assessment, Pedro, please.
Okay.
Welcome. And I'm very curious to hear about what you're going to tell us.
Okay, good morning, everyone. Can you see my screen, just to be sure?
Yes, perfectly.
Okay, perfect. So good morning, everyone. Thank you, Pernilla, for this kind introduction. So my name is Pedro Montenegro. I'm from the University of Porto, and we'll present here part of our work in In2Track3. So as Pernilla said before, we are working in many more things, but today we have some time just to talk about a little part of our work. So this work is being performed not only by University of Porto, so I'm here representing University of Porto, but also Acciona and Network Rail. Sorry, because it's okay. So this part of the presentation is regarding the bridge service capability improvement in relation to the subtask fatigue capability improvement. So the presentation is divided in these 7 topics. So first I'll present the main motivation objectives of this work, then the work regarding the reinforcement with the fiber reinforcement polymers. Then I'll present the numerical model that we are developing and some tests that we perform in the demo bridge. And then some comparisons between experimental numerical properties and at the end some ongoing work to the next year. So why studying fatigue capability improvement? So as you can see here in these graphics that we retrieved from a report from 2008, this is only the example from Germany, but we can see that a lot of steel bridges belonging to the European railway network are already in their design life limit. Some of them, as you can see here, with more than 100 years old. So we
Pedro,
need to... Yes?
Pedro, I think you should be in presenter mode because the slides are not changing. So, and you're probably sharing the other screen.
I'm not
or
changing.
sharing the wrong screen.
Oh, so sorry.
So just change it and go to presenter mode.
But I'm in presenting mode.
Now, perfect.
It's changing now?
Yes, perfect.
Okay.
Thank you.
Sorry.
No problem.
Maybe there was some lag here. Okay. So as I was saying, some of the bridges here, the example in Germany, we can see that some of them are already with more than 100 years old. So we need to study reinforcement solutions. And why reinforcement solutions? So since the bridges are getting old, we have 2 options: or replace the bridges with new ones, which is a very low sustainable solution, both from economic and ecological point of view, or we can try to study strengthening and reinforcement solutions. So of course, here in In2Track3, we are trying to work more in this right side regarding strengthening, and for this particular case that you are studying here with CFRP solutions. So here, the main objective of this part of the work, it includes the evaluation of fatigue life extension of fatigue problem details from a demo bridge, which is the Eastington Bridge in the UK, that was strengthened with externally bonded FRP plates during In2Track2. So here in In2Track3, we are trying to test if this strengthening solution is being is working well or not. Okay. So the demo bridge, the Eastington Road Bridge, it's here in the UK. It's like a bridge with 25 meters span, with some skew here, and it's a bridge with 3 main girders, box girders, connected with these cross girders. Okay. And there is here a detail that is like a fatigue prone detail. I will explain next slide why is a prone detail, which is a detail where the top flange of these cross girders separate from the web. And here we can see here that we have like a decrease in flexural stiffness in this part of the cross girder. So why we are studying this detail? Because there is more similar bridges in the UK. And one of them, the one over the River Tone, which is very similar to this one, and which is going to be replaced. So that's why we are not studying this particular bridge. We are studying a similar one, the one that I talk about. And they already detect, network rail already detect a fatigue crack. So we are trying to work on this type of details to see if with these strengthening solutions can avoid or not these fatigue problems. So regarding the strengthening, so the strengthening has been designed and installed by Acciona. Okay, so it consists on these L angle types SFRP plates. Okay, located here in this part of the fatigue prone detail, and here we have some room in order to inspect if there will be cracks or not. I will talk about later about the monitoring system that was installed last year. So before installing these plates, Acciona made some preliminary laboratory tests in Spain in order to, so they tried to simulate a similar detail, okay? To test a similar detail in the lab and to see if these plates are capable or not of reducing the tensile strain in this area. And from these tests, Acciona reached the conclusion that they could reduce the tensile strains in these locations about 32%. So in principle, this type of solution will give us good results. So regarding the installation on site, okay, so as I told before, the installation, it's these angles of CFERP we can see here in this area. So now this installation that you can see here is not in the lab, is already in the bridge, which was installed in 2021. It has to be postponed due to the pandemic. Okay, and here to try to compare the influence of the CFRP. They installed in two cross girders, okay, and they monitor with strain gauges not only the cross girders with the plates, with the reinforcement plates, but also another cross girder without the plates to try to compare the strains that will occur in these points. Okay, so here are some images of the installation. So the installation took place, as I said before, in two consecutive cross girders, one with reinforcement, another without reinforcement, to try to compare the efficiency of the reinforcement. And this is a permanent monitoring system that is always capturing the results. It has some triggers in order to save the results. So it only saves results when trains pass over the bridge. It has some triggers that detect when the strains start to be a little bit bigger and start to save. And since this is a permanent monitoring system, Acciona Network Rail installed here a cage with a methanol power source, and of course with the data acquisition system. The results from this permanent monitoring system are connected to an online platform that Acciona has access, and we can see in real time the strains that are occurring in these different details, both with and without the CFRP. As you can see here in the right image, you can see that with the plates, we have strain gauges here in this part to detect if there will be a crack or not, but also we are also measuring strains also in the CFRP itself. Of course, in the other cross girder without CFRP, we are measuring in same positions, but in both of the strain gauges are directly on steel. And you can see here some preliminary results. So results measured between November and April of this year. And you can see in blue the results. This is already in terms of cumulative fatigue damage calculated with the SN curves. And you can see here that in blue we have the results in cross girder without CFRP, and in orange and yellow the results obtained with CFRP, in the cross girder and CFRP. And you can already see that we have here 6-month measurements, and you can already see that the reinforcement solution is working well and efficiently. Okay, now regarding the part that Porto is working. So, of course, to try to understand if these solutions work not only in this bridge, but in other bridges in the future, we have to make numerical models to try to represent all these scenarios numerically in order to try to extrapolate these conditions to other bridges. So we developed here in Porto a numerical model in order to perform dynamic analysis and to try to simulate the situations that are occurring in this type of bridges. So we have a global numerical model to perform our dynamic analysis with train passages. But since fatigue is a local phenomena, we also developed a local model of our fatigue prone detail, okay, of the region around the fatigue prone detail. So to perform this numerical analysis, it would be impossible to perform dynamic analysis with a full model with a lot of detail here in the region of fatigue prone detail. So you can perform dynamic analysis with global model, extract the boundary conditions in the around fatigue prone detail, implement the boundary conditions from the response of dynamic analysis to the local model, and work more efficiently in this localized area of fatigue with the local model. Okay, but of course, to rely in these models, we have to calibrate and validate our models. So for the validation, we have 3 steps. So the first step is the validation based on the model parameters of the bridge, which we got from this ambient vibration test that took place between 7 and 9 of June 2022. So a team from Porto and from Acciona went to the bridge, so around 3 months ago, more or less, okay? And we worked together with Network Rail in this installation. So this installation consisted on putting a series of accelerometers in the main cross girders, these blue ones. And these accelerometers are accelerometers that measure, that are very sensitive to vibration. So they are there just to get the ambient vibration caused by winds and by other external excitations. But we also installed accelerometers with a higher measurement range, these green ones, in order to obtain also the response from the trains, okay? But why did you put, that was the challenging part of this test, why did you install only accelerometers in this part? Because we are not allowed, there's a road here in this bridge, below this bridge, with very high levels of traffic, and they didn't allow us to close all the road. So they allow us to close only part of the road and during night, okay? And we couldn't install accelerometers all over the spans. So the challenging part here is that we could install in this region, in first third, because in first third of the span there was here some path that was possible to access, okay? And we installed just in this part, and then we have to compare the numerical and experimental, but only based on the results from the first third of the span, okay? So here's some images of the test. So all the installation has to be took place during night, okay? And we could see here in real time if the ambient vibration that we got from the accelerometers, if we could, with a specialized software that we have here, we could understand if the behavior and the modal properties of the bridge, so natural frequencies, modal shapes, directly based on the vibrations obtained from the accelerometers. So here, apart from the vibrations, ambient vibrations, of course, with that green accelerometers that I showed before, we could also capture the big vibrations caused by trains. Okay, here's some examples that you can see, like here, a train with 5 carriages. You can see here the results, and with 4 carriages. So we have, like, during one day, it was the 8th of June, always monitoring the bridge continuously and getting a lot of results. Okay, of course, this first video, the train is not going this slow, so this is a slow motion video, because you need to take a lot of slow motion videos to try to understand the number of coaches that were crossing the bridge, because now the objective of the next part is to try to compare the numeric and experimental, and we have to have an idea of the type of trains that cross the bridge. So the first result that we already got is the comparison of the modal properties based on the ambient vibration test that I said before. And you can see here that the results are very good. So the numerical model, for example, first, just to summarize some results, the first mode of the bridge with 505 Hertz, we can see here that the experimental almost match these results. Of course, the image that we are seeing here in the right is only the first third of this movement, okay? Because as I said before, you can see that here each of these green and pink points are the position of the star meters, and we could only monitor the first third of the bridge, but you can clearly see that we can extrapolate that this movement is clearly the movement of first mode. Here you have the movement of the first torsional mode, with, okay, here the frequency are not, they don't match so well, but I think we are still trying to improve the model. Here we can see this butterfly mode that is captured quite well by experimental tests, and here the second vertical mode. So this first part, where we try to calibrate the global model based on modal properties, the results are quite good in our opinion. And the ongoing work that you are now carrying out is to not only to validate based on modal properties, but based on dynamic responses. So we have a lot of, as I said, showed before, a lot of dynamic responses due to the train passages. So the levels of vertical acceleration caused by train passages. And we have a lot of events that we captured during that day. So passages with trains with 9 carriages, 8 carriages, 4 carriages. So a lot of them that we can use to validate and to compare the dynamic responses on the experimental and numerical examples. So Network Rail was very kind to give us some characteristics of the trains that crosses the bridge. Of course, there is some uncertainties, because we don't know, for example, for this type of trains, if they are going, if they cross the bridge full or with low, with not so many passengers. So as you can see here, for example, for this example of the class 220 trains, the loads can because there are 2 types of trains that pass there, and you can see here that the loads are quite different, but visually the trains are the same. So what we are trying to intend now, that we couldn't obtain the exact speed that the train passed the bridge, we couldn't obtain the exact trains that cross the bridge, so we are now simulating a lot of events in order to try to match the results with the experimental ones, okay? And of course, we are not only want to validate with the dynamic results, dynamic acceleration responses that we got from these tests, but of course, Axion already gave us access to the results obtained in the monitoring system during that specific day. So we can also try to match the numerical model, not only in terms of accelerations, but also in terms of strains in that specific points that are being monitored by the monitoring system. So thank you very much for the opportunity to talk here, and we hope that these strengthening solutions will work well in this bridge. Okay, so thank you very much.
Thank you very much, Pedro. That was very interesting to hear. I don't know if you've seen it, the rest of you, but I just wrote in the chat that if there are questions on the presentations, write them in the chat, and if there's time left during our presentations, we'll try and answer them now here during the presentation. Otherwise, we will get back to you with an answer. So if you have questions, write them down, and we'll deal with them as soon as we can. Thank you very much, Pedro. I would like to hand over the word to Sergio Cavallaros, who works for Network Rail, or who is a professor at one of the associated universities, actually, but who speaks here on behalf of Network Rail. Welcome, Sergio.
Hi, everybody. I hope you can hear me well and now see my presentation. Thank you very much, Pernilla, for the introduction.
We hear
Can
you
you?
and we see you perfectly.
Oh, that's great then. So welcome. It's a pleasure to be here with you today, representing the great team that we have here in the UK from Network Rail. So the team from Andrew Brown, Adam Glover that are involved. So there are a number of colleagues that are engaging from Network Rail. I'm not from Network Rail, but I work very closely in many different initiatives with Network Rail. I come from Loughborough University, where I am the chair of infrastructure systems. And I'll explain to you today what we've been doing in the space of a patchwork repair in tunnels, right? So this is the purpose of the presentation today. Hopefully we'll have some time for discussion at the end or for questions at the end. So what is the problem? How did this study come to be? So the problem is that we have assets that are in some cases century-old, right? And we need to maintain those assets. In the UK, particularly, Network Rail is responsible for the biggest network of tunnels, and we have a significant proportion of those being masonry tunnels, right? This is what you can see here in this slide. One of the typical issues they face is the identification of areas, localized areas that require intervention, that require patch repairing. And this is what you can see from left to right, the evolution of patch repair process as it happens according to current practice. So it involves a crew of 3-4 workers that will work during night shifts, during the possessions for the repair, obviously not to interrupt the work of the rail network. So they work in night possessions, first installing in the first possession some scaffolding. There are a number of health and safety checks that need to be performed. And then what they do is to remove the defected area, install some formwork that you can see there, already the formwork being installed, and rebuild with new brickwork the area that requires repair, the area that has been removed with the defects, right? Then the formwork is further closed, what you can see here in this this third picture, and they leave the tunnel at that point because the material is not strong enough to withstand itself, and it requires time then to gain sufficient strength. This means that they need to go back and in a different possession to set everything up again and remove the formwork to expose the final repaired area, which you can see on the right side here. This is time consuming, at least 2 possessions. We have 4 people involved. Health and safety is a concern, and there's always the risk that they will overrun and might have impact in the normal service of the network. So the problem is clear. We need to improve this, right? We are still repairing using the same technology almost that has been used to build these tunnels, and we need then to find a solution that is more efficient, more cheaper to deploy, and will allow us to be much safer in the repair of this sort of tunnels. Here at Loughborough, we are world leaders in large-scale 3D printing with robots for construction and repair. And we have in our labs, I think, some of the most advanced robots for this sort of activities, right? And the system set up. So, and we also have other types of cool new technologies for innovation in construction, flexible molding systems, and so on. And the easiest thing for us would be then to try and deploy what we already have, we're already known for, to this problem. But what we usually do in this sort of situations is to recognize that not necessarily the solution that we are more comfortable with is the best one for the problem. And what we did was to scope 37 completely new strategies for the repair, for the patch repair of this particular problem. And we undertook a comparison between this 37 plus a reference, which is the current practice, and undertook a sustainability assessment, considering not only the economic aspect that is clearly relevant, we also included environmental implications, technical aspects as well, and social, because we need to consider as well aspects related to health and safety, how easy would be the solution to deploy the solution. And we have this on the right side, this huge tree with a number of different options that we tested. And without entering too much detail, what you see here is the result of this exercise. I'm not going to enter in the detail, just to let you know, the solutions that provide the highest value here are the best ones. And what we saw is that, interestingly, the ones that we are more known for, additive manufacturing with cementitious materials, for instance, were the ones that provided the worst sustainability, the worst potential. And this was helpful because this drove us to a different direction. Not only one direction, but I have to be honest, several different directions. And amongst the 37, we identified 5 that were promising. And of these 5, we pushed forward 2 of them, right? I'm going to talk today about one of these 2 because both have been developed and taken to a tunnel for use. I'm just going to give you an overview of both, but I'll talk specifically of one. So one that we identified was robotic spraying. So the idea of taking a robot inside and spraying at the void to fill it quickly with a material that sets really rapidly and then allows us to move on, repair more areas, and open for traffic with very little constraints in a single possession, right? It was something that we developed. So we developed this. We developed the robots, and it's different from the typical robots used for inspection. The same robot does both: inspects, decides how to repair, and repairs. So it's the same unit delivering both aspects of the work: deciding and identifying, deciding, and executing, right? So we did it. We took it to the tunnel, and it worked relatively well with some elements that still require improvement because, as you may know, it's complicated to have a system that works integrating with robots that can do all what I've described seamlessly. So we did it and used it in the tunnel. I'm not going to discuss here the robotic spraying. I'm going to enter more in detail in the flexible plate injection. And the idea of the flexible plate injection is very simple. It's a plate that can change shape and accommodate different curvatures in the tunnel. And once we put this plate there, we can inject through the plate or the center or the side of the plate and fill the space with a material that will allow us to open for traffic pretty quickly as well. So this is the solution I'm going to discuss with you today, the temporary flexible plate injection. Then we remove the plate, we continue, go on. So we didn't have any experience in this space, and we started very small scale because we didn't have any prototype or anything that we can use for this application. What you see here are different views of the first prototypes, starting from the left to the right. The first one, the first flexible plate, as you can see, the idea is that the plate can really change shape and accommodate the differences in curvature in the tunnel. Very simple concept, as you can see here, initially with just the plate and some elements that support and push it against the surface of the tunnel for injecting later on. On the right side, you see a slightly bigger version, same concept, deployed by robot at a small scale, tunnel representation, masonry tunnel representation that we had in our lab, right? And this was the concept that we designed and presented to Network Rail. And in discussions, we decided to upscale it. So it was working well. And this was one of the 2 concepts. We have one that this is the mechanical one. We had one that was thermal based, so using temperature to change shape. It's quite cool as well because you just turn a switch and the plate becomes flexible, and you can then turn off the switch after placing it against the surface and it retains its shape. So it was interesting, but energy, power in the tunnel, electricity, having to all these installations would be less less compatible than the mechanical one. So we upscaled the mechanical one for application in a tunnel. And here you have many drawings, and we went through a phase of designing this. And after designing, we set it up. So this is just the base of the plate, what you can see here. So at the wheels that I've seen in the small scale prototype are the yellow ones in this plate here. So remember, we had some wheels that push the plate against the surface. In this case, the wheels are all in the system here, and the plate is not installed at the moment, but it's just the base of the system that you can see here. And the system includes a lot of hydraulics as well, because it's hydraulic driven. So we have a number of jacks that you can see here at the bottom that are responsible for pushing the wheels outward against the tunnel and shaping, giving the plate the shape of the inside of the tunnel. Right, so then you see here the installation and the transportation to the tunnel is what you can see here on the bottom right side. Right, so you see taking the base of the plate to the flexible plate system to the tunnel. Then what we did was trying to simulate the execution of the patch repair. We had some workers. These were the workers in the tunnel, the ones that were there performing other repairs. And it was the first time that they were having the contact with this technology. So you see an RRV here that was brought for the study, and we attached the flexible plate, the back, to the RRV, and run some tests on the jacks. So everything is controlled by the driver. So the driver is able to control the plate itself, how it moves, and the jacks, right? So full control by the driver. And after that, we installed the plate, is what you can see here at the white element that you can see there. So we installed the plate and went to an area to repair the area, as you can see here, is the area to be patch repaired with the RRV, right? So interestingly, when we were there, this RRV was brought for this test only, right? And when it arrived, it was a model is slightly bigger than what we ordered. So the RRV itself was too big for the tunnel, right? This had implications for the test, and it meant that the RRV was so big that it couldn't spin sufficiently to accommodate and place the plate. And we had a spacing of about 10 centimeters to one side. So one side of the plate would be touching when it approached, and the other side would have a space left between 10 and 5 centimeters, right? Because the machine was too big to properly position initially the plate. So the idea was, let's position the plate, and then we push the wheels out so it generates the proper shape, and we can inject through the system, right? But we faced this issue there. We couldn't do it. The machine wasn't the correct size for the application, right? What we then did was try and push the jacks to the maximum and try to compensate for the shortcomings of the machine using the plate. So using the plate for something that it was not intended to. And what we then achieved was, despite the shortcomings of the machine, the plate was able to correct it. So we were able to run the trial despite the problems with the machine, right? Because the plate was designed and could accommodate this sort of imperfection. And this showed us how reliable the system is, how flexible it is. Even when the machine is not the correct one, even when the conditions are not ideal, the plate could accommodate. And this brings a lot of resilience to the system and confidence to the workers that they can make adjustments. And this is super important when you're designing something from scratch, something new. You need to accommodate that. And it was one of the successes of the application. We applied it and it worked really well in different areas. And you can see here a result, not only filling the space, but repointing the bricks around the affected areas, right? So we repaired many areas using the technology. And now we are in a phase 2 of this process. We know we have a plate that works. We are working the design 2 of the plate lighter, more robust, more economic as well. We are working developing the materials and applying the materials, improved materials in the system as well. Although this is not the focus of the next phase, it is more in the injection system. So developing the injection system to deploy these more efficiently. Right, so we already have a system that works, and this is just some sketches of what we are doing in the lab now for the simulation of the void filling with different types of materials, right? And here's some of the walls that we have prepared, and we're running these experiments, which will last until, at small scale, until December. And by January, February, we'll be in a tunnel again with the version 2 of the flexible plate system, the new injection system unit that will be very compact to be able to easily be moved in and out of the tunnel, with a material that can accommodate different working cycles and set pretty quickly. And we'll be doing it in a tunnel again, the revised version of the system by January, February next year, hopefully, right? So just to give you an idea of the improvements that we have already achieved, well, normally I told you that it takes between 2 and 3 possessions to repair one area. We are achieving improvements of the order of 500 to 800% in productivity. So by nearly 6 to 9 times more productivity or more possibilities of repair than we had with the traditional solution. So it's fully justified. Costs are also being assessed and fully justified for improvements of the order of 6 to 9 times in terms of efficiency. So it's pretty impressive, and I think the business model here will really be justified. Thank you very much. Happy to answer any questions if you have.
Yes, there are a few minutes left. Do you have any questions for Pedro or for Sergio? Because I don't think there is anything in the chat. Pedro, I would like to ask you, what would be your next step? If I am an infrastructure manager, how could I utilize the things that you are doing, and when can I do it? Is Pedro gone? Maybe Pedro is gone.
No, I'm here, but sorry,
Oh.
I didn't listen your because my headphones are not working. Can you please repeat? Sorry.
No, my quick question was just that if I am an infrastructure manager anywhere in Europe, and I think this is really, really interesting, how soon can I utilize this? How can I, when can I use it?
Well, in this particular example, so we saw a bridge that there was a problem in one of the bridges, and then we tried to replicate in a similar bridge a strengthening solution that we were supposed to use in the other bridge. So I think these type of solutions are very easy to install. So this CFRP, they install it like in 1 day. So any type of steel bridge that has some problems, or we suspect that we'll have some problems in future, I think it's a very easy solution that you can try to install. So any type of steel bridge that has these type of problems, especially fatigue problems, I think it's a very easy solution to try to avoid fatigue problems.
Very interesting. So it's just to pick up the phone, huh? If one wants to discuss this further with you.
Okay. Thank you.
And Sergio, how is this being used in operation today, or are you still trying and not trying, but are you still working to improve it, or is it the same here? Just pick up the phone.
Yeah. So the solution is, and it's interesting, Pernilla, because we started talking about patchwork repair. The solution is under development, although it has already been deployed, showing that we can repair 3 patches in a single possession instead of 1 patch in 2 possessions. So it's already showing immense gains in productivity, and our idea is to take it even further, be able to do more than 2 or 3 patches per possession with this solution in a much cheaper in a much cheaper way as well. So now we are refining it and improving as well the injection. I think by January, we'll have a very well-wrapped solution that can be deployed in tunnels, and a system that can be taken as a unit and repair different areas as patchwork. But because of the experience that we've had, we are now targeting other systems for consolidation, even without the need to remove bricks. So this is something that is beyond even the current project, and it's a different technology as well, but it's going to have massive implications to the way that we do things in tunnel repair for the future. Huh? So hopefully I'll be able to show some of this in another meeting, but I suspect it will go beyond the project even. I mean, it's the continuation of the project. And I can see there's a question in the chat as well.
Yes, there is a question. It's Samuel who wants to thank you for a very interesting presentation and promising solution. The question is, how does this patch repair affect the load path and the surrounding masonry in the long term?
Yeah, so this is something that we have considered. So we need a material that is sympathetic to the surroundings, right? Ideally, our concerns are around permeability of the system for durability reasons, and also the elastic modulus of the material in the repair. We still have to run more numerical models to understand how this will impact the load path in the tunnel. But with the careful consideration of the material that we are using, I think the impact will be smaller than the reference current practice. So doing what is done now in terms of installing the brickwork back and waiting a number of days to then remove the formwork, this has a bigger impact in the modification of the load paths than what we are doing here. So in that sense, we are improving the current practice, even in terms of load path and structural behavior of the whole system, right? And in part because we do it more quickly as well. We install it and we remove quickly. So it takes us about 1 hour to complete one patch, and it's really quick, right?
Thank you. We have another question here, but it's for you, Pedro. But since we are 2 minutes past here, I will leave that for now, and maybe we come back to it afterwards, because we have our next presentation is Camille from Virtual Vehicle, who will present his whole system model work. So please, Camille, welcome.
Thank you, Pernilla. So I'm going to be sharing my screen, just to let me know by show of hands if you can see or not.
Yes, we see it in, now it's presenter mode too. Thank you.
Perfect. Thank you very much. I'm just going to change here the options. And before I start, I would like to express a deep gratitude to all the colleagues. First of all, to Pernilla for great coordination and for the moderation of today's meeting, and for the great collaboration of all the colleagues that we are working to bring the whole system model to the next level of maturity. Colleagues from Chalmers University of Technology, colleagues at Virtual Vehicle, voestalpine Railway Technology, Material Center Leoben, and Austrian Competence Center for Tribology. Thank you very much. Without you, that work would not be possible. And I've built up the content of today's meeting and the presentation in the following order. So I'm going to be giving the work overview generally, what we are dealing with, and I'm going to present the whole system modeling approach, something that we call VSWSM, to solve numerous problems appearing in the turnouts. And I'm going to be giving you also a couple of track damage calculation results with some important conclusions that we are drawing from that. And we're going to end up with outlook and use cases developed for the next months of collaborative work. Without further ado, what is the work generally dealing with? Our main focus is the railway turnout, specifically the switchblade region and the crossing nose region. And what are we actually dealing with is the track damage, which results from the rail plastic deformation, rail wear, vertical track settlement, and more importantly, interaction between those modules. How do they contribute and how do they interact with each other and contribute to the overall track damage? Very important question to answer. And we believe that benefits to the other works in the field. Not only the research into institutions, also the industry partners can highly benefit of having such a powerful tool to analyze the interaction between the track damaging mechanism, because it hasn't we haven't found anything similar in the literature or neither by the industry. So we believe that such a novel approach to tackle the track damage will be very beneficial and very useful to somebody who is dealing with the turnout's design, service, and maintenance optimization, and generally working with the track damage analysis. How do we solve that problem? We solve that problem by having a framework, something we call the whole system model, or rather approach, so to speak. And I know there's quite a bit of information on this slide, but to read correctly the methodology here, we have to go from top to bottom. So the core of the model is the MBD simulation model, where we have the vehicle modeled and parametrized according to the use case scenario with the specific turnout, as well taking into account the traffic, so to speak, by having the wheel profiles measured and different service conditions identified here and set in the model as well. And the model takes the initial track geometry and the rail profiles, which come as an input, which means we can simulate from the initial installation of the track or from the very specific moment when we want to investigate the development of the track. And the MBD simulation model it generates two different signals here. So one of them being at the low speed wheel trajectories, separately at the crossing nose and the switch plate, which comes as an input to VTI simulations, where VTI stands for vehicle track interaction, where we simulate the track settlement due to the dynamic forces. The model delivers back here the updated track geometry, and it's been reinitialized, and the model operates in a new loop, so to speak. In the same manner, we perform the dynamic simulations and we generate the wheel rail interface data to perform the rail damage simulations in a crossing nose and a switch blade to account for the profile change due to the wear and plastic deformation, and model delivering back updated rail profiles. The whole system is being reinitialized again, and then we can simulate the amount of traffic we're interested in. And in this exercise that I'm going to be showing you, we were simulating two different loops. Initial track up to 2 MGTs, updated all the parameters, track geometry, rail profiles, and simulation of the second loop. And we observed and we did the important conclusions how the track actually develops and how those mechanisms are interacting with each other, and contributing to the overall track damage. And a little bit information without too much details about the MBD simulation module here. So we're working with the well-known and well-validated, so to speak, verified Manchester benchmark model as a basis. One of the exercises that we learned under supervision of Jan Bezan and Professor Paulson from the Chalmers University of Technology and University of Huddersfield. We also use the very popular track model here based on the Swedish turnout with a radius of 760 meters and the crossing angle 1 to 15. And we also account to the different variation of the wheel profiles, as you can see the example here. And this is what the track actually sees when it comes to the measured profile, so to speak, or CAD data in our case. A couple of words to the VTI simulation model, just to give us a short idea and snapshot of what the model actually is capable of doing and consists of. VTI model, something we call the vehicle track interaction model, consists of 1/8 of a vehicle being on top of the rail, which is modeled as a beam and has a discrete sleeper support. It gives us the advantage that each sleeper can actually have its individual stiffness, height, and which are subject to the calibration based on the field measurements, and also each individual settlement properties. So the model is quite flexible in simulating the track settlement, and it delivers the sleeper forces to the settlement model, in which we operate with a phase 3 to be confident in a mostly linear phase, delivering back the sleeper settlement, and then the iteration loops are being repeated. What is interesting in our case studies, we investigated the effect also of the different track stiffness profiles, namely variable track stiffness profile when we have higher stiffness under the crossing panel, and also the constant track stiffness, which can be achieved by using the elastic support, for example, under sleeper pads. And we've also investigated the effects of that. A couple of words to the rail damage simulation models. They're both based on the finite element methods and operating it within the different internal steps, so to speak, ideologically including the dynamics, meta models of the elastic plastic contact damage evolutions, and then smoothing of some profile change. In the crossing nose, in the same manner, finite element method based models are operating in the switch panel as well, by using also the extrapolation algorithm to increase the performance of the module, being also calibrated against the multi-axially loaded stress control tests. a couple of results and a couple of insights that we were able to achieve to understand the behavior of the model, so to speak, behavior of the track. Main findings here, if we analyze the wheel trajectories, we can see that the set of measured wheel profiles are actually showing the varying wheel trajectories at the crossing panel and at the switch. And also updated wheel profiles due to the wear and plastic deformation affect the vertical motion of the wheels. And we can see the exact change of trajectories subjected to the rail damage, so to speak, between the different loops simulated at the switch panel and at the crossing nose. Important information to know. Also, most importantly, we also know the behavior of the contact Q forces, the way they change and the way they increase, specifically at the region of the crossing panel here, at the tip of the crossing, as well as in the switch panel. We can also see, not only see the qualitatively how those forces are being evolved as we operate, as the track is being in operation, we also see the values on how those amplitudes are changing. So it's a very powerful tool to analyze further and do further statistics, so to speak. When it comes to the rail damage evolutions here, for the two different track stiffness scenarios, we're seeing that the important information here that the plastic deformation dominates it compared to the wear and simulated traffic. We also see the plastic deformation rates being attenuated over time as we move along in the track operation. And we also interestingly see that the constant stiffness case shows generally lower shape change area rate. So which can be important information also for somebody who wants to optimize the track performance and to reduce the track damage by using different techniques into developing the track stiffness along the turnout, so to speak. In the same manner, we see the same observation for the switch panel, seeing the significant profile change within the initial MGTs of the traffic, mega growth stones. And beyond that, we see the stabilized profile change. And also the plastic deformation is being identified as a decisive mechanism governing the overall profile change within the initial traffic that we've simulated. Interestingly, combined effect, if we analyze at the switch panel, crossing panel with the constant track stiffness and the variable track stiffness, not only we can see that the switch panel track damage is actually much lower as compared to the crossing panel, mostly due to the lower dynamic Q forces. We also can see that the values of the subsequent increase of the track settlement is kind of a little bit more in the case of the constant track stiffness as compared to the variable, but generally we achieve less track stiffness as compared to the variable track stiffness when we use the constant track stiffness. And not only we can see the general behavior of the model, we also have exact numbers, so to speak, to quantitatively validate and to quantitatively describe the performance of the different cases of the track. We also have developed two different cases where we've used the nominal rail profiles only and also including the updated rail profiles after 2 MGTs. And what we found two interesting things here, that while using the variable track stiffness here, we're going to see the higher track degradation rates generally, and identifying also two different regions of the track behaving linearly pretty much until 20 MGTs of the traffic and then starting behaving non-linear in both cases. And we also find out that the rail profiles change contribute more and more to the track settlement, which results also in self-reinforcement behavior of the track. Very interesting knowledge there. And just the whole conclusion here, which can be interesting to read when I'm going to distribute the slides also among the participants here. Very interesting insight into rail damage analysis, track settlement effect on the crossing nose, and also the combined effect of the rail damage and track settlement analysis. This is all interesting, but how this can be actually validated and applied to the specific use case scenario. So we've talked about that through, and we've pretty much closed the whole loop here. And we started thinking about the real case application, so to speak. But before going to that, I would like to also point out what is the use of all the information, all the conclusions that I've just shown you. Well, I believe, and we believe generally, that the benefits for the railway industry is going to be lying in the operational and maintenance cost optimizations by having the time-efficient predictive whole system track damage model, which can account for the major damage mechanisms, effect, and their interaction also interestingly. And by having that tool, we're gonna be able to address major cost generating problems in railway turnouts, which we as know, according to the case study done by the colleagues from Voestalpine, are pretty much like an iceberg. So we have to concentrate a lot of forces to analyze an optimized system when it comes to the costs for maintenance, replacement, and reducing the downtime, so to speak. By having a tool so to speak, time efficient turnout performance and LCC optimization tool by having the whole system model. And it also gives a little bit advantages as we use the modular approach, as I've shown you. So because more modules can actually be incorporated in the future upcoming projects into VSM, which gives the flexibility to which critical damage mechanism is actually to be accounted for specific turnout design and specific region, as we have a vast variation also according to the climate within the European Union only. And so to speak, the different mechanisms can also be included as a rolling contact fatigue, break contact tips, and ramping and tradition. And then we can start doing different system optimization when it comes to material selection, switch crossing panel, switch and crossing nose geometry optimization, so to speak, and also track bedding optimization, giving important advices to the producers and to the network operators. And currently we are performing a couple of tasks here to demonstrate the use case of the model. And for that, we've chosen the shift rail turnout demonstrator placed in Vienna, leasing. And for that, we're choosing the turnout number 4, which also been optimized, and we want to investigate the results here, putting the main focus on the track settlement, rail damage, and wear. And here you can see the technical drawings generally of all the installed turnouts here, as well as the satellite images, with a lot of different instrumentation performed by Voestalpine, ÖBB, and Getzner. And so we've talked with colleagues that we identified different critical zones here. The drive unit and the switch panel, the crossing panel with a lot of different instrumentation and sensors placed there, and the transition zone here between the long sleeper and short sleepers generally. And so we've set up the different measurement data requests, so to speak, identified the driving scenarios, and also took additional data to parameterize our models, vehicle turnout models, and to validate the whole system model, so to speak. A lot of data, as you can imagine, and so we have to do the structural analysis of the data. For that, we're mostly working with the turnout rail profiles here and the train passages with the sensor data by performing the comparative analysis between the simulation results and the field measurements. And the model that I described before is now being reparameterized to mimic the ER20 locomotive, which was used also for the measurement campaign, which results in the parameterized MBD simulation model. When it comes to the track, we're also using the shift rail demonstrator turnout data, reparameterizing the track and implementing the measured rail profiles there. So this is the current work it's being in underperformance. Additionally, we have also developed internally the algorithms for the automatic realignment of the profiles as we receive the data in the raw format, and then we can generate different scenarios in the through and diverging road, so to speak, by having this tool also to align automatically the measured profiles, and which come as an input automatically also to the co-running track model for the MBD simulations. There is a work that's being performed also with the train passages scenarios. Out of the whole timetable of all the measurement campaign, we were able to identify the most critical and relevant scenarios here for the facing move, trailing move, and both facing and trailing moves here. So 12 different scenarios that we can simulate. And currently we're working with the MBD model testing with a 120 kilometers per hour speed in a through facing direction. And a couple of preliminary results that I wanted to show here of between in the comparison, a little bit comparison between the Chalmers University of Technology results and the VIF results. We're trying to also do analysis of the co-running track model performance as compared to the structural track model, and those are the initial results. And we're going to be also doing the further refinement and further workflow within the VSM here as well, something that I wanted to mention here. So, and also as well is going to be wrapped up also with a comparative analysis against the field measurements of the turnout. Yeah, so with that, we're going to be completing the whole VSM framework, having the MBD simulations and VDI simulations calibrated, and also thanks to the colleagues from the Tribology Center, AC2T, we're going to be also achieving the better performance. So if we just analyze the block here in the right bottom part, we're going to be also achieving better performance by having developed the meta models here to try to find the replacement for the field element methods to achieve better the reduction of the bottlenecks, so to speak, to move from the order of weeks to the order of hours and to align the overall VSM model performance. And we're going to be able to do that by having the meta models developed and calibrated using the test rig data generated by the AC2T colleagues. So thanks for that collaboration as well. So with that, I would like to wrap up for now as time is ticking. And again, I would like to thank the co-authors without whom this work would not be possible, and for the contact and for the questions you can contact me directly, any of my colleagues, and also maybe better Pernilla and Michael from the Michael Speer from the virtual vehicle. Thank you for your attention. Please feel free to ask some questions, as there probably has been a lot of interesting topics that we can also follow up, discuss with that.
Definitely. Thank you so much, Camille. As you said, there is really some flexibility in this schedule. So if there are any questions for Camille, please feel free to ask them. Otherwise, we move on to the next part of this. Are the wheel geometries also updated in the loop, similar to the rail profiles, Camille?
Yeah, thank you for this question as well. So we are using this set of wheel geometries, which are pretty much constant. So we're not doing the updates. They're measured, and then they're used within the whole iteration of the loop. So they're not being updated. They're just used the way they are, as we believe the wheel profiles are not subject to as severe changes as compared to the rail profile changes within the initial traffic, so to speak. I hope that answers your question.
Good, thank you for that, Camille. We have a last part of this presentation today, which is actually more than one part, because there are several, I can just show you. No, I want to, it's the rail inspection part that we have, where we have put together several topics that are really being performed by several of our partners, but it will be Vincent Chartier from Relanin who will be presenting this, because they are in his work packages, and to make this smooth and keeping things together, we would like to have Vincent presenting all of these. It's smart material, as I mentioned previously in my short session, and thermal stresses, rail stiffness, the EMAT sensor, and the autonomous trolley. So we will have a block now. This is the final block for a half an hour with rail inspection. So please, Vincent.
Yeah, thank you, Pernilla, for the introduction. Going to share my screen. Hopefully, should work. Is it working? Can you see my screen?
No.
Not yet.
Not yet. No. Oh, yes. That should work.
Yes, you are in. Yeah, you're in PowerPoint mode now. So if you just switch to presenter mode, then we'll be fine.
There you go.
Perfect. Thank you.
Okay, thank you. Thank you. Good morning, everybody. So, as Pernilla said, I'm Vincent Chartier, and I'm a project manager for Relenium, and I have in charge the work package 2 and work package 4 of the In2Track3 project. And within the work package 4, we are looking at new technologies for rail inspection. And so I will present you some of the new technologies that we are studying. And so I've prepared this presentation with the help of my colleague Antonio from University of Minho in Portugal, Shane from the Technical University of Delft, who works for ProRail in Netherlands, Hugo from Infraestruturas de Portugal, so in Portugal, and Melanie from Network Rail in the UK. So first, why are we studying new technologies for rail inspections? Well, as it was previously mentioned, there are a huge stack in to improve the life cycle cost of the maintenance activities, because we roughly estimate that the maintenance represents between 70 to 90% of the life cycle cost for the rail or turnouts. So there is a we have to focus on that if we want to have a cost-efficient railway network. And secondly, we also need to improve the availability of the assets, because sometimes we have to stop service in order to make the maintenance activities. So these new technologies will aim at reducing the time for the maintenance, and also to improve the quality of the rail inspections. And finally, it was also mentioned previously by Sergio. There is a question of safety, operator safety when maintenance operation takes place, because unfortunately it can happen that there are some accidents, injury, or even worse, that could happen. So these are the three main aspects, three main issues we want to address and to improve by studying new technologies for rail inspection. So what are we looking at when we're talking about rail or track inspection? First, we are studying two technologies in order to monitor the track stiffness, which is directly related to the track geometry. So we obviously need to monitor that the geometry of the tracks doesn't change, doesn't move in a too important way. So to do so, we're studying technology based on our box acceleration, and also a new self-sensing material. We're also looking at monitoring the rail thermal stresses by using ultrasonic waves. Another technology that is studied is the image sensors that will be able to detect the rail surface defects in a new way. And finally, we developed an autonomous trolley, well, in order to make some rail inspection without people, in order to increase the safety and to avoid accidents that could happen. So we'll give you a short overview of each of this technology. And so I will start with the axle box acceleration system. So this techniques is developed by the Technical University of Delft for ProRails. So just to give you a background about what kind of measurement, what kind of techniques or way of measurement are used so far to measure the track stiffness. There are three ways to do it. First, you can put some sensors on the sleepers, but obviously, if you put sensors on each sleepers, it will be it will be very costly. So when we do that, you have to focus on discrete location. So it means you could miss some defects on the part of the tracks. The second method use specialized measurement vehicles. So here you can monitor the whole tracks, but At the moment, it operates at very low speed, so you disturb the traffic, and so you cannot you're not able to do it very frequently. So it's the main drawbacks of this system. And finally, there's also a, existing of train-borne measurement system, which are located in service train. But so far, these techniques measure the overall stiffness of the tracks. So I mean it measure in just one stiffness that represents the rail pad, the ballast, and the foundation layer. So you cannot identify which part of the tracks is in default, or you cannot monitor one layer at. You can monitor only one layer at the same time, and these techniques are also not so robust. So we want to improve that by using a method based on the axle box acceleration sensors that are located in the wheel of the in-service trains, and so it is based on this measurement and also based on models. So this is, as Pernille explained at the very beginning of the presentation, it's a continuation of the In2Track3 project because the proof of concept was done during this project. So the goal of the In2Track3 project for this method is to validate the method and carry out some in-field test in order to reach a TRL 5. And basically, just in few words, the approach of these techniques is to use a model that define a model of the tracks that define a library of possible track stiffness and track displacement based on different loading on the rail, on the track. And on the other side, there's the measurement made by the ABA sensors, and so these two inputs are handled within the data-driven models that can determine the stiffness of each layers of the track. So where are we now on this topic, on this study? So the vehicle track interaction models has been developed, and the data-driven model is almost completed. There's only, we estimate, about 20% left until the end. And the first field measurement have been carried out this summer in Sweden. So you can see some picture of the test in Sweden. And the remaining work is as follows. So we have to finalize the data-driven model. So this should be completed by the end of this year. And there will be some additional tests that will be done in Netherlands by the end of this year. And finally, there will be the calibration and validation of the models that is planned for the first quarter of 2023. And so this study is working well, and we are on track with the plan. So this is it for the ABS system. So just come back to the list of the technologies we are working out, and I move to the self-sensing materials, which will be also used for the track stiffness monitoring. And so this study is led by University of Minho and with infrastructures de Portugal. So what is this new, this innovative system? The principle of this system is to use or to insert or to mix piezoelectric nanomaterials to mix them with cement and sand and to insert this new what we call self-sensing geocomposite to insert it in the track structure below the ballast, for instance. And so because of the nanomaterials property, so it will translate, I would say, the load of the train into electrical signal. And this signal will be used to monitor the damage on the tracks that occur on the track's stiffness. So this will allow to make like very big sensors because it will be like several meters or several tens of meters sensor long. So we plan to apply this in the transition zone where or in the critical zone of critical area of the track. So it will improve the accuracy of the monitoring because at the moment we could do it only on a discrete location with some sensors. So we will be more accurate, and it will be also more cost effective because this system doesn't need any battery, for instance, and so it will require less maintenance operation. So within In2Track3, we aim at enhancing the results of In2Track2, and to do so, we will make two full-scale demonstrator, and we will be able to reach the TRL7. And the approach is to first to make some laboratory test in order to optimize the geocomposite, and next, or in parallel, we're doing some numerical simulation that will help to calibrate and validate the system. Next action is also to define and study the acquisition systems. It means the interface between the materials and the software and the remote data storage. And finally, we will build the two full-scale demonstrators. So where are we at the moment? So the numerical simulation have been completed, have been performed, as well as the acquisition system. And the demonstrator location has been defined, so it will be located on a Portuguese network. And here you can see the drawings of the demonstrator. So the first demonstrator will be located in the transition zone between a bridge and an embankment. And so the sensors, if we can call it like this way, will be like 22 meters long, and it's 5.5 meters wide and 20 centimeters thick. And the second second demonstrator will be over an hydraulic pass, and the sensor will be only 14 meters long. And the remaining work for this study is to complete a lab test in order to to fine-tune the self-sensing geocomposite. It's also to validate to finalize the demonstrator specification. So this should be completed by the end of this year in order to start the building of the demonstrator in the beginning of 2023. And so this should take about 3 months, and then we will calibrate the models and validate the systems during the second and third quarter of next year. So this activity is also progressing well, and we were on track with what was planned. The third technology I want to introduce you is ultrasonic waves. So in order to measure the thermal stress on the rail, and so this study is made by a network rail. So what is the problem with the thermal stress is the problem is that if in case of the weather is too hot, there's rail deformation, and so you can face a risk of track buckling. And in case of the weather is too cold, then you could also face rail breaks. So we need to monitor the stress that the rail has to face. And at the moment, the way to do it, either it uses a destructive way, or either they are slow and not so accurate. So there's a need to improve that, and the way to do it is to use ultrasonic waves. And so network rail is studying two methods that use this ultrasonic waves. So first, there's a method called birefringence, which is represented in this sketch, in this drawing. And then there's another method that is called a universal method that uses angles. So that uses sensors which are located at specific angles, and there's also within this universal method, network is studying the influence of the angles. So here again, it's a continuation of the In2Track3 project, because the proof of concept was validated during this project. And for In2Track3, we want to make some in-field test in order to reach TRL 6 or 7. So, and the approach for doing so is to first develop some mathematical models, then to make some laboratory trials in order to show the relationship between the stress and the speed of sound of the waves. Then there will be some full rail trials. And for the birefringence method, we plan to make the trials on multiple rails, sorry, in order to assess the influence of the rail. And finally, there will be some tests carried out on the infield in full scale. In full scale. So far, the laboratory testing has been completed, and we made some first full rate testing. So you can see here the installation of the test rig, where there are the two method that is that are installed. And so the first results are quite positive, at least for the birefringence one. For the universal method, they still need to make further investigation. And what has been noticed also is that there is quite a high sensitivity of the setup. There is a quite sensitivity of the yes of the setup on the accuracy of the results. And we have also found the location for the track demonstration. And so we need by the end of the project to complete the data analysis from the full rate test, to improve the setup in order to improve the accuracy and repeatability of the system. And there will be further tests on the birefringence method, and finally in 2023 we'll make the track demonstration. So here the work is almost on plan, but we have to make further work that was not planned in order to improve the accuracy of the method. So I move to the fourth technology, which is what we call EMAT sensors, EMAT1, and the aim of this technology is to improve the rail surface detection or inspection. So this study is led by Relenium. And why are we doing that? It's because at the moment, so the rails inspections is usually made with the use of sensors that need to be in contact with the rail. So I'm talking about ultrasonic or eddy current technologies. But so this contact can be difficult to ensure, and it's also it can also be costly because we need to for when for instance, when the ultrasonic sensor is installed on a train, we need to use a couplant like water in order to ensure the good contact. And this sensor can also be sensible to pollutants or oxidation on a rail. So the solution that is studied is to use a contactless sensor, which are called EMAT. So it stands for electromagnetic acoustic transducer. And we plan to we want to use them on a remotely controlled trolley. So you get some picture here of the defaults that we want to detect. So mainly head checks and squats, and also cracks. And so within In2Track3, we will make some tests with a in-field test with prototypes in order to reach TRL 6 or 7. So the approach is to use existing EMAT sensors in order to be more cost efficient. Then is also to design a dedicated trolley that will be equipped with these sensors. And so this trolley will be remotely controlled by a smartphone. It has to be easy to transport and to mount. And it has also, you must have the ability to control in real time the distance between the rail and the sensors. Then we'll plan to make infield tests in order to set up all these systems, and also to make some infield tests in order to validate the defect inspection that uses IA algorithm. So the results up to now are the following ones. So the trolley has been manufactured. We've done the first drive setup trials, and the algorithm that will be used to develop to detect the defects have been developed. And we also done some first rail inspection in-field trial at Eurotunnel last month. And what is remaining is to finish validation of the sensor liftoff control. So the liftoff is the distance between the rail and the sensors. We plan also to make a second campaign of test, which will be dedicated to the rail defect detection. And then in 2023, we will use the measurement campaign in order to enhance the algorithm. And so we are also on track with the plan. And finally, I will present you the technology of the autonomous trolley. So this work is led by Network Rail. And so, as I mentioned before, manual inspection can be required on the tracks. So this can be this could lead to safety issue, and we could also improve the cost by using an autonomous trolley, and manual inspection actually is required when we make ultrasonic inspection with trains, because they cannot identify the precise detail and location of the defects. So the solution we are looking at is to design an autonomous trolley, which will have the following functionalities. So first, it shall be able to inspect a significant length of the track, and then returning at the start point, and so without operator control. And then it will be able to confirm the defect that was identified by the ultrasonic inspection train. And then it will identify precisely the location of the defects, and it shall be able also to mark where the defect is. And finally, it will produce a down-level summary of the defect location and depth. So this work is here again, it's a continuation of the In2Track3 works, and it's also made in collaboration with the In2Smart2 Ship-to-Rail project. And so for the In2Track3 project, we aim at making infield test in order to reach here again TRL 6 or 7. And the approach is is to use and to combine existing technologies, which are the command and control system that is developed in In2Smart2. Also to use existing ultrasonic inspection system, and also artificial intelligence that is used for data analysis. And finally, the approach is to design the vehicle platforms that will be used to install all the materials, and also to design the communication system between the different brick of the system. So up to now, we have purchased an electric trolley that is used as a basis for the study. The rail inspection system and the IA control system have also been selected, and we have also identified the location where the track demonstration will be made, and this track has the particularity that the defects on it are well known, so it will be easier to validate the autonomous trolley performances. And so the remaining works are to complete the ongoing pieces of work, which are to adapt the control system, and also to install the In2Smart2 command and control system, to develop the communication protocols between the inspection equipment and the IE analysis and the control and command systems, and also to design the physical connection to couple the ultrasonic trolley to the electric trolley, and also we plan to manufacture artificial defects. So, and finally to make track trials, so that will occur that will happen in 2023. So here again, the progress is good on this topic, and so we are on track with the plan. So that ends the presentation of the quick overview of the inspection system. So if you want to have further information, I give you the contact here on the slides, and you can contact them to get further additional information. Okay, so that's it.
Thank you very much. Thank you very much, Vincent. We have
Yes,
3 minutes left, and you have a question from Camille here. I would be interested in which rails are going to be the subject for testing parametric studies.
Which, sorry? I'm sorry, I couldn't get.
Which rails are the subject for testing or parametric studies, as mentioned in some of your slides? And what's the criteria for choosing specific rails for such testing procedures?
I'm sorry, I don't. Which I mean, there's no specific rail. I mean, I guess it depends on which technology is. The question is related to, but there's no specific rail. I mean, it's a plain line rail mainly, but.
Okay, well, maybe we can take this question later on. We have 2 minutes left. If anyone has any more questions, or you need information specifically on the project or something, please contact me and I will guide you to the person who should answer the question if it's not myself. We have 1 minute left. All of you have been made presenters. Can I ask all of you to turn on your camera so we can take a nice snapshot of the meeting today? That would be fun to have, and I would really enjoy that. Could you please do that so we can make a short presentation, short snapshot? And you are more than welcome to take your own snapshot as well, because I mean, since it looks differently in all of the places that we are. But since it doesn't seem to be so many who wants to turn the camera on.
It looks good.
Okay, it looks good. It doesn't. Okay, it doesn't look good at my on my computer. So if everybody just waves hi, and we'll take a picture. Are we good, Mats?
Yes.
Perfect. Thank you all so much for attending today. Thank you all who presented for your brilliant presentations, and thank you for all the brilliant work that you are doing. It's a pleasure working with all of you, and you will hear more from us. Thank you, everybody, and take care. Bye.
Bye-bye. Thank you very much.
Bye.
Thank you.
Bye. Thank you.
Bye.
See you next time.
Thank
Bye-bye.
you. Bye-bye.
Bye.
Bye-bye.
Thank you.
Bye. Thank you.
Bye, thank you.